Okay, so today we're going to be talking about a very interesting aspect of special relativity, time dilation. And one of the things I love about special relativity is the math is not actually very complicated. It only requires high school trigonometry. But the consequences are really profound and mind-boggling. So let's get started. Before we start our thought experiment over here, we're going to set up this very special clock that works on the fundamental constant, the speed of light. And so I have a bottom mirror here and a top mirror over here. I have my laser, and I'm going to measure a time unit to be the amount of time it takes for it to hit the top mirror and then come back down to hit the bottom mirror. And so for special relativity, there are two important principles to keep in mind. One is that the speed of light is constant in all inertial reference frames. I'm just going to abbreviate that. And then the second important point is that the laws of physics are the same in all inertial reference frames. Now the first principle is a little strange because if I'm running at 5 meters per second and I throw a baseball at 5 meters per second relative to me, you on the bleachers will see that baseball travel at 10 meters per second. But if I'm running at 5 meters per second and I shine a flashlight, that light travels away from me at 3 times 10 to the power 8 meters per second, the speed of light. And you on the bleachers will see that light travel at the exact same speed, 3 times 10 to the power 8 meters per second. Now the second law is also a little bit peculiar because if I trapped you in a box so that you couldn't see outside, there would be no experiment that you could do to determine whether you're moving at 0 meters per second relative to me, or 30 meters per second, or 60 meters per second relative to me. As long as you're moving at a constant velocity, there's no physical experiment you could conduct to figure out what velocity you're traveling at. So with those two principles in mind, let's get started. So I'm going to be on the train here. This is me on the train. I'm going to New York or something. And I'm here with my handy dandy light clock. And this light clock is not moving relative to me. So it just goes up and straight back down. And the height of this light clock is L. So I measure my time unit to be the distance the light travels divided by the speed of light. So 2L, because it goes up and back down, divided by the speed of light, C. Now you, as an outside observer, will see something a little bit different. So I'm just going to draw these at 2 different time intervals, 3 different time intervals. I'm just going to draw the mirrors because with the trains in the picture it'll get a little bit messy. So you can just imagine me in the train along with these mirrors. Alright, so that's the bottom mirror, top mirror. And these are 3 snapshots in time, where this is t equals 0. This is t equals t prime. Because you're a different observer, I'm just going to denote you as t prime. And you measured the time to be the amount of time it takes to go up and back down. So when it goes back down over here, that's t equals t prime. Because you're traveling at a constant velocity, when it hits the top meter, that's halfway through. So that's t prime over 2. And the light travels up to the top mirror along a diagonal path and then back down in a diagonal path. So how would I represent the time that you measure? Well, the height is the same, it's still L, but now we have this horizontal component that we have to take care of. Well, it takes t prime over 2 units of time to get through here. So what is the distance? Well, the distance is just the velocity, in this case the velocity of the train, multiplied by the time interval. So this distance is just vt prime over 2. So I can express the distance the light travels using Pythagorean theorem. So the distance light travels is just the square root L squared plus V squared T prime squared all over 4. And because it has to make a return journey back to the bottom of the mirror, I'm just going to multiply that by 2. The same principle applies to measure the time. So T prime is the distance light travels, in this case it's this, divided by the speed of light. And because of our first principle that we talked about, the speed of light is the same in all inertial reference frames. So this is going to be c as well at the bottom. And so I'm just going to do a little bit of rearranging. I'm going to move that c to the top on the other side, L squared plus V squared T prime squared over 4. I'm going to square this to get rid of the radical. Radicals are always annoying to deal with, so we're going to get rid of those. And now I want the T prime squareds to be on the same side. So I'm just going to move my V squared T prime squared term over. Now I'm left with this. So I'm just going to transfer this to a new piece of paper before it gets too unwieldy over here. I'm just going to copy down what we had at the last time. T prime squared minus, let me move that down for you, V squared T prime squared equals 4L squared. Now I'd like to express this answer in terms of T naught and T prime. So first I'm going to, before I go any further, I'm going to factor out this T prime squared. And now I want my T prime factor to be expressed in terms of the T naught that we found in my reference frame. And if you'll remember, T naught was equal to 2L over C. Well, how do I get T naught into this equation? Well, if you'll notice, 4L squared is just 2L, the numerator over here, the whole squared. So I need a C squared at the bottom so that I can bring in my T naught term. Well, I have a C squared right here. So let's factor that, pull that out of the factor. C squared divided by C squared, 1, V squared divided by C squared. I'm just going to write that down like that. It was 4L squared. I'm going to move the C squared over. So I get T prime squared 1 minus V squared over C squared all over 4L squared over C squared. Now we're getting somewhere. So I'm just going to substitute that in from what we had previously. This 4L squared over C squared is just 2L over C the whole squared, which is just T naught squared. And now we solve for T prime. So I'm moving this factor over and taking the square root, and we're left with this equation. Now you'll see this means that the faster you go relative to the stationary observer, the slower time passes for you relative to the stationary observer. You can see why we don't see this in our everyday lives. Because if v is really small, which it is in our everyday experience, v never gets close, the velocity never gets close to 3 times 10 to the power 8 in our everyday experience. This factor is basically the square root of 1. And so T prime is approximately T naught and we don't notice a difference. But let's say V approaches C, gets very close, like say 0.5 C. Then we actually see some of the dilation effects we were talking about before. Alright, ladies and gentlemen, there it is. The equation for time dilation. The faster you move relative to the stationary observer, the slower time passes for you relative to that stationary observer. Hopefully in subsequent videos, I'll be able to talk about a few examples and how special relativity works in the real world, and also some of the other aspects of special relativity like length contraction and the nature of simultaneity. But for now, I hope you learned something and I hope you enjoyed this video. Thank you.